Hey guys, welcome back so fast. Cool. So this is a little bit of a shorter video than what we had from before. What I want to go over is the following. We're going to be studying things called actions in this class, and actions are the quantities which will give us equations of motion to understand what a classical, like how a classical system gets its dynamics. That involves the, understanding calculus of variations. And calculus of variations, like I said in the last discussion lecture, is pretty, it's both straightforward and pretty complicated at the same time. So basically, we're going to be studying things which are defined in terms of integrals over some integrand that depends on the coordinate we're integrating over, namely x, and then functions of that coordinate. And usually we're only dealing with functions of the coordinate and the first derivative of that same function with respect to that coordinate. So it'll look something like this, and there's going to be bounds of the integral as well. Great. So one thing I want to point out is that this can have x dependence that doesn't show up in y of x or y prime of x. So what that means is that when we're actually studying what are the extreme values of the extreme values y, which are functions of this functional s, x can show up in funky ways. And so I wanted to go over two examples to show why you need to be careful of where x is showing up and how that actually can affect your answers. So one of the systems I'm going to study is the following. Let's say we just have a over 2 cos squared kx. So this x is showing up not as just the argument of y, but as a function unto itself, y squared plus 1/2 y prime squared. So what I want to do study is this and see what are the Euler-Lagrange equations, what should we expect, and contrast it with studying this. So basically move the x dependence over to the other term. So here, just to be clear, a is going to be a constant. K is going to have dimension of inverse x. Cool. So regardless of what your dependence is on x, the way that we derive the Euler-Lagrange equations basically is oblivious to it. So the Euler-Lagrange equations don't care if there's some extra x-dependent terms that show up in the integral. So there's still this. But notice if the x shows up in front of a y and y's only, it just basically acts like a constant. If in this integrand L, the x is showing up in front of y primes, we're taking derivatives of the partial derivative of the integram with respect to y prime. That means that the x dependence actually ends up looking different than if it showed up in front of y's. So let's do example A first, and I'll show you exactly what that means. In example A, dl dy prime is just equal to y prime, which means that d dx of dl dy prime, which is one of the terms that shows up in the Euler-Lagrange equations, is just equal to y double prime. dl dy is equal to minus a cosine squared kx y. Cool. So basically, again, the the Euler-Lagrange equations in this case were oblivious to the x dependence as like actually, it basically acted as though it was some position dependent constant. So what that means is for the Euler-Lagrange equations, they're equal to y double prime is equal to minus a cosine squared kx times y. Now, solving this differential equation is another story that's much harder because of this term that depends on x. But we're not going to get into that here. We're not actually going to try to seek a solution. What I wanted to do is contrast this with taking a functional derivative where the cosine squared kx is showing up in front of y prime. Cool. So in that case, dl dy is equal to minus ay for equation b, and instead dl dy prime is equal to cosine squared kx y prime, which means that when I take a derivative with respect to x of dl dy prime, right, dl dy prime has an extra x dependence in it. So I need to use the product rule. So what that means is I'll have a cos squared kxy double prime, but there's also going to be a minus 2 k cos kx sine kx y prime. And so what that means is that the Euler-Lagrange equations are going to be cos squared kx y double prime minus 2 k cos kx sine kx y prime is equal to minus a times y. Again, this is actually a very hard differential equation to solve. However, what I wanted to contrast is that depending on where the x is showing up, it actually very measurably affects what your work is going to be in leading up to just getting the differential equation. And so it seems like a little bit of a pedantic point, but I think this is actually something that a lot of students trip up on the first time that they're going through this. So I thought that this would be a pretty good introduction just to some of the basics to complement some of the more complicated stuff that I'm going over with these lectures on chapter 6. Cool. With that said, my next lecture is going to be a little bit more in depth. What we're going to go over is when you have functions of multiple variables instead of just one variable, how do you actually generalize this calculus of variations to accommodate that setting? Cool. All right. So I will see you then.